So the first two pieces of advice are always the same. Do problems and take care of your health. The more problems you do, you'll start spotting patterns. And a lot of what we do in this part of Calc 2 is, all right, there's all these different tests you have for convergence. There's so many tests, you want to be able to spot like which test you use right away. So if you look at some of the recent exams, one of the things they would do is they just say, look, here's 5 series, just tell us converge, diverge, and just boom, boom, boom. They want you to just be able to whip that right out. And the way you do it is you practice. You look at problems and you start to spot certain things. Oh, it's like this is geometric. Or, oh, this looks like a P-series. Or, hey, let's get rid of the noise. So anyways, keep practicing. Do your problems. And yes, do take care of your health. Physical health, mental health, all kinds of health are greatly appreciated. And I hope we'll get through all the problems in 2 hours. I think we can. At least we'll get really close. But we'll definitely get all the problems done. We're not going to the last one is fun. So, find the exact value of the following sum. Now, I'm going to say the following. If you see any question that says the phrase, find the exact value, you automatically know 3 things are in play. It's geometric, it's telescoping, or it's a Taylor series. That's it. So anything that says, I need you to find the exact value, you have one of those 3 things has to happen. So if you see that phrase, be on the lookout. So in our case, what do we have? We have the sum, n equals 0 to infinity of 4 to the n plus 5 to the n plus 6 to the n, all of that divided by 10 to the n. Now, the thing here that we see is geometric. Whenever you see powers of n, or something to the nth power, you say that's geometric. But you have to rewrite it in a way that's more convenient. Now for us, the addition upstairs, very convenient. That really says we can break it apart. So 0 to infinity of 4 to the n over 10 to the n plus 5 to the n over 10 to the n plus 6 to the n over 10 to the n. Now, they might do something really mean, which is give you a sum that diverges and then the answer is infinity, but very, very unlikely. So we strongly suspect these should converge. And because they converge and everything's positive, we can really think of these as 3 sums. So sum n equals 0 to infinity. And 4 to the n over 10 to the n, you want to write that as like a single term to the nth power. So in this case, it'd be 4/10 or 2/5 to the n. The next one, n equals 0 to infinity, 5/10 to the n, which is simplifies to 1/2 to the n. And the last one, n equals 0 to infinity of 3/5 to the n, which is 6/10. Now, in general, we have the following. The sum from n equals 0 to infinity of r to the n is 1 over 1 minus r. And this is as long as the absolute value of r is small. And so we are in the right form. So 1 over 1 minus 2/5 plus 1 over 1 minus 1/2 plus 1 over 1 minus 3/5. Because all of these are the right form. We all start at the right place, and it's of something to the nth power. So 1 minus 2/5 is 3/5. If you flip it, that becomes 5/3. 1 minus 1/2 is 1/2 downstairs. You flip it, that becomes 2. Here you get 1 minus 3/5 is 2/5. You flip that, becomes 5/2. You can get a common denominator of 6. So you get 10 over 6 plus 12 over 6 plus 15 over 6, giving us a grand total of, if we can do math, which hopefully we can, 37 over 6. Now, that being said, you may not have to simplify. Look for instructions. If your instructions do say simplify, make sure you simplify. If the instructions don't say simplify, well, don't have to. You might want to, just out of habit. But be careful. Whenever you simplify, you open up yourself to a danger. Now, here's something you should keep in mind. We know what you know. See, and now you know that we know what you know. And so when I say that is we know what you're looking for, and we might do things to throw you off. So as an example, suppose you look at number 2. Again, this is a find the exact value of something. 1 over pi to the n minus 1 over pi plus 1 to the n. Now, the reason I say we might be trying to throw you off is if you glance at this and you don't think hard, you might think, oh, this looks like telescoping. Because telescoping, you have like that n and that n plus 1. What we're doing is we're obfuscating. We have that pi and that pi plus 1, which has nothing to do with telescoping. So be careful, don't let us catch you off guard. So what do we have? Well, the answer is we have similarly what we had before. Namely, these are geometric sums. So this sum I can think of as two pieces, 1 over pi to the n, and then minus the summation n equals 1 to infinity, 1 over pi plus 1. I guess I should put my parentheses here, to the n. Now, you might notice our sum starts at a different place. In general, if you have a geometric sum, then what you get is the following. The sum of a geometric series is always the first term in your sum, wherever you start, over 1 minus r. So when we wrote down the formula just a few minutes ago, we had r to the n. If we started at 0, you get r to the 0, so your first term was 1, which is why you got 1 over 1 minus r. So here, our first term would be what happens when you plug in n equals 1 in. So you'd get 1 over pi, that's our first term, divide by 1 minus r, which is 1 over pi, minus, then here, 1 over pi plus 1 over 1 minus 1 over pi plus 1. And for here, we can definitely leave this as is. If you felt the need to compulsively simplify everything, you can multiply the first term here by pi over pi, and that would leave you with 1 over pi minus 1. If you did it to the second term multiplied by pi plus 1 over pi plus 1, you would end up with 1 over pi plus 1 minus 1, or if you like, 1 over pi minus 1 minus 1 over pi. And I think that's about as simple as you could get. If you really wanted to go further, I suppose you could get a common denominator, but yeah, I think that's good enough. All right. Another find the exact value of. Now this one looks a little bit different. Find the exact value of the summation n equals 0 to infinity of the integral from 0 to 2 of 1 over 1 plus x plus n quantity squared dx. All right, so we have to figure out what this sum is. Now, looking at this, we say, all right, let's just work through this kind of like an onion here, one layer at a time. So this is an integral that we recognize. In fact, it's a pretty straightforward integral. Do you recognize the antiderivative of 1 over 1 plus quantity x plus n squared? I hope so. Yeah. If you've been spending any time at all with me, you know Steve is going to try to get an arctangent in there at some point. Arctangent of x plus n evaluated from 0 to 2. So what do we have? So this is really the sum, n equals 0 to infinity of, well, you plug in 2, you get arctangent of n plus 2 minus arctangent of n. All right. Now, this shows you what kind of thing we're dealing with. Namely, this is the right setup for the telescoping. So in general, if I have a telescoping, what do I have? Well, telescoping has something along the lines of the following. It's a summation from n equals some starting point to infinity, f of n plus some k minus f of n. This is what a telescoping series looks like if you rewrite it in the certain form. So essentially it's just saying that there's an offset going on. We can actually see that here the offset is 2, which means that when we are writing out the terms, and we'll write down the first couple of terms, we'll see that it's terms 2 off cancel. Now, one of the things to keep in mind with telescoping series, oftentimes these involve things with partial fractions, where they took an expression and then they put it back together. Well, partial fractions helps you pull things apart, so be open to partial fractions. And another thing about telescoping series that we've caught people off in the past, so let's not catch you. You're the good students, so what's another thing to be aware of is be careful with the tail. And in particular, when I'm talking about be careful with the tail, is what happens to the n. And what happens to your, I'll say f of n as n goes to infinity. When the terms are going to 0, then what that says is, oh, I just have to keep track of what's left at the start. When the terms don't go to 0, you have to be a little bit more careful. Now, let's find out what situation we're in. So if we have our sum here, well, we start, that'd be arctangent of 2 minus arctangent of 0. That's their first term, n equals 0. Then add, then it's arctangent of 3 minus arctangent of 1. And then the next term will be arctangent of 4. Oh my gosh, my arctangent handwriting is getting terrible. You'd think somebody who loves arctangent so much would be really good at writing arctangent. Arctangent of 2, and I'll write one more term, arctangent of 5 minus arctangent of 3, and then there's the dot, dot, dot. Now what's happening here is we see a couple of things. Well, because of the offset of plus 2, that means you should expect that terms that are 2 off will cancel, and we see that. This arctangent of 2 cancels with this arctangent of 2. This arctangent of 3, go over 2 terms, cancels with this arctangent of 3, and so forth and so on. So that most of the terms will cancel. What doesn't cancel? Well, what doesn't cancel are the terms at the start, and there's 2 terms that'll be left over if your offset is 2. If your offset is 3, there'll be 3 terms, and so forth and so on. Then you have to be careful about what happens at the end in the tail. So the arctangent of 0, we can handle that. That would become 0. And arctangent of 1, that becomes negative pi over 4, because we know what arctangent of 1 is. Now, if you were not worrying about the end, you'd be like, okay, and there's my answer, negative pi 4s. But when you look at the problem, it's like, I don't think I should be getting a negative number. Because I'm integrating something which is positive, then I'm adding up a bunch of positive stuff. How can I end up with a negative? Unless this is one of those weird infinity paradoxes. But no, it's not an infinity paradox. It's because of the tail. So what happens to the tail? So what you have to do is, if these terms go to 0, if fn goes to 0, then you are happy. You just keep what's at the start. If fn doesn't go to 0, then you look at the partial sums. And then you work with that. So what that means is, instead of thinking it as the whole infinite sum, you say, I'm going to keep going, and then I'm going to actually stop some way down the line. So when I look at a partial sum, what I'll have left is I'll have the terms at the front that don't cancel, which is the 0 and the negative pi over 4. And then what I'll have is the terms at the end that don't cancel. The terms at the end that don't cancel, because my offset here will be 2, I'll have an arctangent of, say, some n plus 1, and plus some arctangent of n plus 2. This is what a partial sum looks like. So this is, if I look at the sum from n equals 0 to capital N of my expression. So now everything else canceled out. All the other terms, there was cancellation, except for 2 at the start, 2 at the end. We know what happens at the start. What happens to arctangent as you head off to infinity? What does it do? Goes to pi over 2. And of course, if I add 1 to the inside, it still goes to pi over 2 because it's still heading off to infinity. And therefore, our answer is pi minus pi over 4, which gives us our final answer of 3/4 pi. All right. So that one is one of those, whoops, pay attention, be careful. Be the right amount of careful. All right. Number 4. To determine whether the following sum converges absolutely, converges conditionally, or diverges. Well, one thing we can roll out right away is the conditional. And the reason we can roll conditional right away, there's no alternating sign. The only time you can have something converge conditionally is you have to have a plus or minus. So we know it's definitely not converged conditionally. So it's either going to converge absolutely or it's going to diverge. And this is one where we want them to be really careful and make sure we're doing our test. So it says, look, we can't just do something. We have to actually give a name to test. So we look at our expression, and more or less the big idea is we want to say, we want to try to compare things to things that are easy for us to handle. So generally things like p-series are good to handle. We can think of integral tests, ratio tests, and so forth and so on. But you always start by looking at the expression. You say, okay, cosine of 1 over n to the n squared. And you ask yourself, what is it doing? What happens to that term? Because ultimately, the real question about whether or not something converges or diverges says, what's happening? How quickly is it going to 0? Because remember that we have that one test that says it has to go to 0. If it doesn't go to 0, it can't converge. So convergence is always about how quickly it goes to 0. So that's what you're trying to figure out. By the way, should it bother us that we start at 72? No, we could start at 1,000,000. It doesn't matter. It's not the start that's the problem. It's that infinity. Infinity. You pay a high price for it. Well, let's try to get a handle on this. So let's actually see, first thing you should always check, if you're not quite sure what's happening to this, have like an idea of whether or not it even goes to 0, check to see if it goes to 0 or not. Because if it doesn't, we're done. So let's do a quick test. So we're going to take a limit as n goes to infinity of the individual terms, cosine of 1 over n to the power n squared. Now, if you take this limit, you see that the cosine is really going to like cosine of 0, and so that's 1. Then n squared, that's like infinity. Well, 1 to the infinity, this is what's called indeterminate. In other words, you just can't look at that expression and figure it out. So indeterminate expressions are ones that are not automatic. So if it's indeterminate, what do you need to do? Do you remember for indeterminate? Yeah. Le hôpital. Okay, so we've got to channel our inner le hôpital. All right, so be prepared. You might need it. Okay, so let's let L equal our limit. And the reason I'm doing L is to use le hôpital, I've got to have a fraction. Right now, no fraction, no le hôpital. So the way I get a fraction is to bring this exponent down. But to bring an exponent down, the only way I can do that is to get a log. So the log of L is the limit as n goes to infinity, log of cosine 1 over n to the n squared. But now I can pull the n squared down, and I'll go ahead and pull it really far down, so far down it goes all the way to the denominator. So cosine 1 over n over 1 over n squared. Now it's going to 0 over 0, and therefore we can apply le hôpital. So we apply le hôpital. This becomes the limit as n goes to infinity. Well, log cosine would be, 1 over cosine, 1 over n, times the derivative of cosine, which is negative sine, 1 over n, times the derivative of 1 over n, which is negative 1 over n squared. And that's going to be divided by the derivative of 1 over n squared, which is, if you do that, minus 2 over n cubed. Because I can think of 1 over n squared as n to the negative 2 power. Negative 2 comes down, and we get n to the negative 3. And I can already get nervous here because I see I'm taking up a lot of space. I hope that this gives something interesting. And then we'll be like, aha, and there's our work. Well, let's see what happens. Well, what do we have? Well, we can make some observations here. We certainly have, here's an n squared. I can cancel off two of those n's. There's a minus there. This 2 is a constant. I can go ahead and pull that out of the limit. So 1/2 limit, n goes to infinity. There's another minus. I'll go ahead and pull that minus out. And now I think to myself, well, what do I really have here? I have cosine of 1 over n. I know what that does. I have sine of 1 over n. And then I have a 1 over n. I say, oh, wait a second. Time for me to flex my math memory. Because I remember something about this. So cosine 1 over n, that's no problem. That goes to 1. Sine 1 over n divided by 1 over n, what does that do? Also goes to 1. It's like that expression, sine x over x. As long as the inside part of the sine matches what's underneath it, and those things go to 0, that thing goes to 1. So we say, aha, l'hôpital, you genius. Now, remember this negative 1/2 is not our answer. What is our answer? Well, we go back and say that's the log of our answer. So that says that L, our limit, is e to negative 1/2. Now, you might say, okay, so is that the sum? No, it's not the sum. What have we just found? Well, what we found is we have that this piece, so cosine 1 over n to the power n squared goes to e to the negative 1/2. So it's our individual terms are going to e to the negative 1/2. But what's important about e to the negative 1/2? Yeah, it's not 0. Since the terms do not go to 0, then, and we have to name our test, I believe there's a couple of names for it. Some people call it the nth term test. Some people call it the basic divergence test. Whichever way you remember it, but you have to give it a name. If I can spell test. Series does not converge. Or we could say series will diverge. Okay, so we're done. So be open. It might be the case that you might encounter something where the terms don't go to 0. Don't automatically assume that everything goes to 0. And if it's not automatically obvious, just do a check and be prepared. And the L'Hôpital is very good at fixing these things. Look out for things like indeterminates. If you ever see something that's like, I don't know what that is, that's an indeterminate. And you're like, well, that's the L'Hôpital. Hope it works.
Why is 1 to the infinity indeterminate?
Well, 1 to the infinity is indeterminate because, of course, infinity is not really a thing. And the thing is, it's really like a number very close to 1 to a number that's very big. And that can be made close to any kind of value you want, depending upon how close you are to 1 versus how close you are to a really big number. And by modifying that, I can make it approach essentially any positive number I want. So that's why it's called indeterminate, is because depending upon how the base, the bottom part gets close to 1 and how the top gets close to infinity, it can approach anything.
So I guess would that apply to any number that goes to the infinity, or would it have to be the same thing?
If it's 2 to the infinity, it's infinity. Okay. If it's 0 to the infinity, it's 0. It's 1. 1 is that really pesky number. So if it's anything less, if it's between 0 and 1, and it's to the infinity, it goes to 0. If it's anything bigger than 1 to the infinity, it goes to infinity. But 1, it just depends on how fast things move. So determine whether the following sum converges absolutely, conditionally, or diverges. Again, we can rule one out automatically. Which one can we rule out? Yeah, conditional. So if there's no alternating sign, it cannot be a conditional convergence. So we look at this and say, all right, well, we don't worry about where we start our sum. So that's not a problem. The 17, that's not a problem. So what do we have? We have like 1 over n, and then something much smaller, which is log n, and something like really, really small, log n, squared. Okay, so we have to figure out what is the right test for us to use to determine whether or not this converges. Now, hopefully, you should recognize this test, because I will say that by now, there's a test which is hyper-specialized after we reach a certain point. 1 over n, if the other stuff wasn't there, what would we say about 1 over n? Do you remember that? It diverges, it's the harmonic sum. So it's just a little bit bigger than n downstairs. And the question is, of course, the n is right on the very edge between converging and diverging in terms of the p-series. So the question is, does this little bit push us over? So as a rule of thumb, if you see stuff that looks like n and log n, log n, and so forth and so on, this is a signal that says integral test. So integral test is basically built almost hyper-specialized for this situation. The reason I say it's hyper-specialized for this is the integral test got us to p-series. And so anytime now we can compare it to a series where we have like n to a power. If that power is less than 1, we're good to go. The integral test tells us if it's bigger than 1, we're great to go. It's right on that dividing line where the integral test says, well, got to get into it a little bit more deep. So we do the integral 1065 to infinity of 17, and replace all these n's by x's, x, log x squared dx. The 1065 you don't care about. The 17, again, we don't really care what this value is. The only thing that we care about is whether this value is finite or not. That's our goal. Now, if you're doing some sort of approximation, the integral is an approximation to the sum, but right now we are not doing any approximation, so we only care about whether or not this integral converges or diverges. So, do we see a good substitution to be making here? I think there is one. Okay, I'll just take log x. It's sort of like you go into the worst thing, the one that has the most layers on it. So in this case, it's the one with the log. If it was just a single log, like that, then that u equal log. If there was a triple log, make u equals log. And you might say, does anybody other than mathematicians care about things like log? And the answer is no. I did know a mathematician who actually his email address was like log@gmail.com. So, but only mathematicians would get the joke. Oh well. Oops, I'm sorry, I haven't updated this. Okay, so we're going to let u equal log. And so what does du become? Well, we follow the rules. So the derivative of the outside, the outside function is log, so it's 1 over the inside, which is log of x. Then you times by the derivative of the inside, which is 1 over x, and then dx. So what happens is that this 1 over x log of x dx, that becomes our du. Then this other part is going to become u squared. So we're going to get 17 over u squared du. And as we head off to infinity, log heads to infinity very slowly, but it still goes there. And then we have this annoying term downstairs, log of 1065. That's not so important. The important thing is we can integrate 17 over u squared. And if you integrate that, you get minus 17 over u. Because you can think of u squared in the denominator as u to the negative 2. So you add 1 to the exponent, that would be u to the negative 1. So that's why you get a negative in front, because we're dividing by that negative 1. And the u downstairs is u to the negative 1. And we evaluate what happens at the start doesn't matter. The real question is, what happens up here with this infinity? So, negative 17 over infinity, what do you get? Get 0. Yeah, and of course, we know that you can't actually plug in infinity. So when we talk about negative 17 over infinity, it's like, what happens to negative 17 over u as u goes to infinity? But, we know what we mean. We're good enough now. So we end up with 17 over, because we get 0 minus log 1065. But the only important thing about this is that this converges. So now we can say, since the integral converges, then by the integral test, sum also converges. Because the integral test basically says these two things, the sum and the integral, are going to have the same behavior. And they're either going to both converge or both diverge. And I will say that really at this point in time, because of everything we've learned with p-series, this is when the integral test really comes into its strength, is when you have something like this. Because we have all these other things which help. We have things like limit comparison, which gets rid of noise, and then we have p-series. So this is about the only case where integral tests come into play. Yes?
Would you ever use like the limit comparison test if you had like a nastier expression, since that would be considered noise?
Yeah, so would we use the limit comparison test? Yes, so sometimes you can use multiple tests together. And I think we'll see an example like that later on. So essentially, the limit comparison test is great at getting rid of anything with a plus sign. So you can get rid of what we call lower order terms. And then it might be the case that after you do a limit comparison test, you don't actually get necessarily right away to an answer, but you say, here's a simpler sum to work with. And now in that simpler sum, maybe an integral test works, or maybe a root test or a ratio test, depending on the situation. But yes, you should almost always, if you see things like plus or minus coming into play, you think, there should be like a limit comparison test at some point. Okay, number 6. Determine whether the following sum converges, absolutely, converges conditionally, or diverges. The sum, n equals 1 to infinity, cosine pi n over 5 times the cubed root of n plus 3 times the fifth root of n. Okay, and then we have to name any test used. Now, can we eliminate one of the tests right away? Well, got to be careful. See, we're hiding something. What's true about cosine pi n? Alternates. Really, cosine pi n is secret code for minus 1 to the n. It's a way for us to make something that looks like, is this really converging? Yes. Or rather, I should say, is it really alternating? Yes. So be careful. Be careful. Sometimes we hide it. So it might be something that converges conditionally. So, we forgot to say, on this previous test, we said converges. We should have said converges absolutely, because we said that was what we needed to say. All right, my apologies. All right, coming back to this one. Well, can we tell whether or not this converges as is? So whenever you have an alternating series, what does the alternating series test say? So you need to basically look for a couple of things. Does it alternate? In other words, do you change signs, plus, minus, and it does. And then you say, okay, what happens to 1 over 5 times the cubed root of n plus 3 times the fifth root of n? What do we need to be true? Well, not that it's greater than 0. It does need to be greater than 0, because we've taken off the alternating part. It needs to go to 0. So the alternating part says, I need to alternate, and my terms need to go to 0. Now, technically, there's a little bit more, in that the terms have to go to 0 in a nice monotonic fashion. We're not going to test you on that. We're basically wanting to see, can I see that the terms go to 0 or not? And we'll be happy enough with that. So both these things are true. It alternates, the terms go to 0. So this converges. It's a converging sum, which means we can eliminate now diverging. But we're not done with the problem yet. All we know is that it converges, and it converges if we include the plus minus, but it doesn't tell us whether or not it converges absolutely. So to tell whether or not it converges absolutely, let's look at the following sum. So consider the summation n equals 1 to infinity of not negative 1 to the n, but just 1 over 5 times the cubed root of n plus 3 times the fifth root of n. So now what we want to do is we want to do some sort of test to see, does this converge or does this diverge? So now is our time to shine. All right. Well, maybe not our time to shine, but our time to think about what's a good test. And what I like to do is I like to say, look, if you've got a plus sign, that means there's noise. So let's get rid of the noise. And the way we get rid of the noise is we use limit comparison test. So we ask ourselves the question, which one of these two terms is bigger? The cubed root of n or the fifth root of n? The cubed root of n is bigger. And so what we can do is, by limit comparison test, and what we compare it with is we look at the highest growing terms. And the numerator is just 1, because it's a constant. Downstairs it's n to 1 cubed. This converges if and only if the sum from 1 to infinity of 1 over the cubed root of n converges. So we can reduce it down by just saying, let's just break it down to look at the highest growing part. Does this sum converge? This sum by, all right, does this sum converge or diverge? This sum diverges. Why? By a p-series. Because this is a p-series where p equals 1/3. And so 1 is that borderline. And if you're anything 1 or below downstairs, then you're going to diverge. Which means, so the sum n equals 1 to infinity, 1 over 5 times the cubed root of n plus 3 times the fifth root of n also diverges. And now we go all the way back and said, okay, now that's if we take off the alternating part. So our final conclusion is that the original sum needs that alternating sign, so it is conditionally convergent. If we take away that plus minus, it won't converge. So make...
Do you need a limit comparison test, or is that just the direct comparison test?
Well, the thing is, if you do a direct comparison test, you have to get something that it is underneath it, that's smaller than it, that you know will also diverge. And so if you can come up with something that you know for sure, here's something that I know guaranteed is smaller than this sum, then that's great. And there are times when comparison test works better than limit comparison test, but not very often. I think that limit comparison test should be like one of your main go-to tools. So the limit comparison test says, let's get rid of all the noise and focus in on just the parts that are giving us the best information.
I was asking if you actually didn't take a limit.
Yeah, I know. We mentally did it. I'm sorry. By limit comparison test plus mental computations. Is that
when would you not use limit comparison test? When would be a bad idea to use it?
Well, when would it be a bad idea to use limit comparison test? There are occasionally some sums where it's just hard to sort of nail down what the limit is. So you could have something like, so this is not part of the problem, so I'll put a little box here. Ignore what's in the box. This is not part of the solution. So not part of problem. In case anybody's reading this. Now, of course, if they're reading this, they wouldn't be listening to my audio commentary about how this is not part of the problem. All right. You could have something like the following sum. So it's like sum 1 over 3 plus sine of n to the nth power. Now, the problem with this part right here is 3 plus sine of n doesn't really converge to anything. It moves up and down all the time. And so infinitely often it's pretty close to 2. Infinitely often it's pretty close to 5. Because sine of is going between -1 and +1. And because of that, I can't do a limit comparison because it's not really limiting to something. And so that's why you want to be careful to run limit comparison. It's not a end-all, be-all. But in this case, what you can do, and I should have thrown some terms here, 1 to infinity, you can say, well, wait a second. I can say that 1 over 3 plus sine of n to the n. Look, the worst case scenario, 3 plus sine n, it's never going to go below 2. So this is always going to be below 1 over 2 to the n. And now I can say, okay, I can do a comparison with the test where I know something that definitely will converge. Because 1 over 2 to the n converges, it's geometric. So that's an example of a case where limit comparison would be a hard thing to do, but a comparison test would be an easy thing to do. But I would say, I would be satisfied if you do limit comparison where you just say, take the highest order terms. Because that's what we do with limit comparison tests. So even if you don't officially do a limit, if you're saying, look, I'm just grabbing the highest order terms off of each piece, and we know that, okay, highest order terms, all right, that's great. That's what you're doing when you're doing a limit comparison test. Speaking of limit comparison tests, okay, so I know it feels like we're doing a lot of these questions about does this sum converge or diverge. The reason we're doing that is because that's a lot of the time that we spent in the last part of the course about whether or not something converged or diverged. We will get into non-converge diverge questions pretty soon. In fact, I think the next one gets us out of the converge diverge category. So here, this is really a chance for us to be like, intimidated. But we're not going to be too intimidated. We're going to work through this expression. So we have this crazy looking sum. And there's even a -1 to the n. And so at least it's alternating. No, that's something. So we have 2n factorial plus 100 to the n plus n to the 100. Then we have 3 to the n plus 20 log n. And then we have like n to the n, 10 to the 100, and that's squared. And then we have n plus 1 plus n to the 4th times 2 to the n. Now, really, the big thing about this problem that you're being tested on is, do you understand how do different sizes of things compare? So one of the things that you're looking at is you're trying to understand what's happening to the behavior as n goes to infinity. So you need to know how do the sizes of things compare. In other words, which ones dominate which other ones. So to sort of give you an idea of what I mean is here's sort of a rough scale. N to the n is very big. So it's a lot bigger than n factorial. So if I have n to the n, that's going to grow faster than n factorial. If I have n factorial, that's going to beat any exponential. So c to the n, and here where c is just some number big one. It doesn't matter what it is. It could be a billion to the nth power. N factorial will eventually beat it. So factorials beat exponentials. But exponentials totally trash n to a constant. And this is for any constant. And of course, n to any constant really beats a log n. And so this is just a couple of things. So just, it's sort of like the big ones that we often deal with are exponentials beat polynomials, factorials beat both of those. And then if you have an n to the n and you had to compare it to n factorial, n to the n will beat an n factorial. So the reason I'm saying this is whenever you see something with a lot of plus signs, that says do a limit comparison test and get rid of all the noise. So we're going to use limit comparison test to remove lower order terms. And so in our case here, well, we go through and say, all right, first off, if we're going to do a limit comparison test we're not going to include the negative 1 to the n. Limit comparison test did not talk about alternating sign. So I'm going to be focusing on the sum of just the parts that are positive. 2n factorial plus 100 to the n plus n to the 100. And then I have 3 to the n plus 20 log n. And I'm going to divide that by n to the n plus 10 to the 100 squared times n plus 1 plus n to the 4th times 2 to the n. Okay. So here's my sum. So this converges if and only if, well, now what we go do is every single term, we just pick out what's the highest growing term. So I have 100 to the n to the 100, and 2n factorial. Factorial is going to beat those other two. So from the first piece, it's 2n factorial. Then the next piece, I have 3 to the n, and I have 20 log n. Log n grows very slowly, very, very slowly. So 3 to the n is going to win. So 3 to the n. Downstairs, I have n to the n versus 10 to the 100. And you're probably thinking, hey, 10 to the 100, that's 1 with like 100 zeros. I would love to have that many zeros in my bank account. Well, you probably do. You just don't have the 1 in the front. So 10 to the 100 is a monster big number. But it's nothing compared to n to the n in the long run. And therefore, what wins off of the first piece is n to the n squared, which is n to the 2n. And then we finally have n to the 4th times 2 to the n, because that beats the n and the 1. So that's our expression. Okay, so now, by limit comparison test, we remove the lower order terms, and we said, I can reduce it down to this kind of a sum. How do I tell whether or not this sum converges? What's the right test to use? And how do we know? Ratio test. Yes. And there's a key that will always be there. If you ever see a factorial, when you see a factorial and you're doing a test, that's a ratio test. Because that's it. The only thing that you know how to handle factorials with are ratio tests. So we say, okay, I see a factorial, there's a ratio test in my future. So I'm thinking of this as my a sub n. And so we apply ratio test. And we're going to look at the limit as n goes to infinity, a sub n plus 1 over a sub n. So here is where we get to be very patient with our arithmetic. Well, no big surprises. Whenever we come here, everywhere we see an n, we put an n plus 1. So we get 2 times n plus 1 factorial, 3 to the n plus 1. Downstairs we get n plus 1 to the power 2 times n plus 1 times n plus 1 to the 4th times 2 to the power n plus 1. That's my a sub n plus 1. A sub n is just what I have already, and since I'm dividing by it, I can just take the reciprocal. So n to the 2n, n to the 4th, 2 to the n, divided by 2n factorial 3 to the n. Now there's a couple of things that happen here. Well, we look for, so let's point out what's going to happen. The reason the ratio test works so well with factorials is this is really 2n plus 2 factorial. And I can take 2n plus 2 factorial and I can rewrite that in the following way. Namely, I can write it as 2n plus 2 times 2n plus 1 times 2n factorial. So in other words, I can keep pulling terms off the front until I get down to 2n factorial and say, aha, perfect. That will cancel with what I have below. In a similar way, 3 to the n plus 1, I can write that as 3 to the n times 3. N to the 2n, I'll leave that as n to the 2n. N to the 4th, I'm okay with. And 2 to the n. Downstairs, well, what do we have? We have n plus 1 to the 2n plus 2. I'm going to write that as I'm going to think of this as there's an n plus 1, an n plus 1. So I'm grabbing two n plus 1s off of this piece. There's a 2n factorial, which I'll put underneath the 2n factorial. There's a 3 to the n. Then over here, that's where I'm going to put the n plus 1 to the 2n. We'll come back to that in a second. Then I have n plus 1 to the 4th. And I have this 2 to the n plus 1, which is really 2 to the n times 2. So I've accounted for everything. And I've just sort of tried to line things up in a way that is very convenient. The reason I say it's convenient is we get cancellation. The 2n factorials cancel. That's why we wanted to do this test. 3n's cancel. The 2 to the n's cancel. And we get some things happening. So for instance, what do we see here? Well, if I look at this part, 2n plus 2 over n plus 1, that's going to go to 2. Because I can think of it, it's a polynomial over polynomial, same degree, I just grab the leading coefficients. 2n plus 1 over n plus 1, that's also going to go to 2. 3 is going to go to 3. N to the 4th over n plus 1 to the 4th, that's going to go to 1. Because they're both, n to the 4th is the leading power. And so if you grab the leading powers, it goes to 1. The 2 is going to be a 2. So that takes care of everything except one little piece. And that little piece there. And I guess I should point out that this 2 really is downstairs, so it's a 1/2. All right. So let's do a little work to the side here. So this is, what do we have? Limit as n goes to infinity, n to the power 2n over n plus 1 to the power 2n. You prefer to have the n plus 1 upstairs over the n downstairs, but that's easy enough for us to do. We'll just move the n to the 2n all the way down. So it's like 1 over n plus 1 to the 2n over n to the 2n. Okay? I've just basically 1 over the reciprocal. And the reason I'm doing this is I'm getting up to a certain point. Because there's a particular limit that you should be like, I've seen this before. So that's 1 over, and I'm going to put this together, and n plus 1 over n is 1 plus 1 over n, and then I'm going to have to the power 2n, which I'm going to think of as n squared. So here's the limit that you should recognize. 1 plus 1 to the power n. That should be something you just know. Do you know what it is?
E.
It's e. And because of the 2, that says that our answer is e squared. So this part here, this it's 1 over e squared because that's in the denominator. This part here is 1 over e squared. So if we put this together, what do we have? Upstairs we have 2 times 2 times 3, which is 12. Downstairs we have 2 times e squared. Well, what is e squared? Well, e is about 2.7. It's a reasonable approximation. So what's e squared about? Good question. I should have written down a hint here. Okay, so e squared. All right, fine. We'll do this. Normally, if we, on a test, where we didn't have a calculator, we'd give you a decimal approximation. So let's see, e squared is about 2.7 squared. If you square 2.7, you will get 5.89, I believe, approximately. Something a little bit less than 6. So 2 over e squared is less than 6. Okay. So what about 12 over 2e squared? Well, what does that say? It's greater than 1. So what's the conclusion? Well, by the ratio test, this is going to something above 1. Now that's bad. If I squared this right, did I square it right? Is it right? Now I'm nervous whether or not I squared this right. Should it be that low? No, it can't be 2 point. Okay, hold on. I think I squared this wrong. What's the square of 27? 540 plus... Yeah, I got that number wrong. Okay, hold on. 7.29? Yeah. I was off by 1.4. Yeah. 7.29. Okay, so 2 times that is like 14 point something. So yeah, it's not greater than 1. It's less than 1. Phew. Okay. We would not expect you to know this in an exam situation. We would give it to you in an exam situation. I should have given it a hint. Of course, if I put a hint in, it gives away all the fun. All right. So, converges by ratio test. Now, what converges? Well, the answer is what converges is this sum. This n equals 100 to infinity of this sort of compressed sum. But that converges if and only if this sum converges. But this is the original sum without the minus 1 to the n. So what's our conclusion about the original sum? So original sum is absolutely convergent. So if you take off the, whoops, I can't spell absolutely right, but all right. If you take off the plus minus 1 and it still converges, it's absolutely convergent. This is more challenging than probably we would put on an exam. Unless I were writing the exam, but I'm not writing the exams this semester. So next semester, yeah, don't retake it. Just pass. Okay, so, all right. Let's start picking up our pace a little bit, otherwise we're not going to even get close to 2 hours. Find the interval of convergence of the following sum. So for the interval of convergence, we basically start by doing the following. So there's a process. The first thing you do is you either apply a root test or a ratio test, and that gives you everything except endpoints, which you apply some test which is not root test or ratio test. If the root test or the ratio test works on the endpoints, you messed up the root or ratio test to get your interval. Now, I have, for some reason, discovered that kids these days, you young people, you like to use that root test. So that's okay. So we'll do the root test. So how does the root test work? The idea is you say, okay, I'm going to think about this as my a sub n. And I'm going to look at the limit as n goes to infinity of the absolute value of a sub n to the 1 over n. So this is going to become the limit as n goes to infinity. And we take the absolute value. That'll be absolute value of x minus 4 to the 2n over 9 to the n. Then I have n to the 1/2. And this is all to the 1 over n power. So that's the limit as n tends to infinity of absolute value of x minus 4 squared. Downstairs, I'm going to get 9 to the n to the 1 over n, which is 9. And then I'm going to get n to the 1/2 to the 1 over n, which has n to the 1 over n to the 1/2. So the only place where the n shows up now is this piece right here. And this is one of the limits you should know. What happens as n goes to infinity of n to the power 1 over n? Goes to 1. And you should know it. You should also probably write it down just to say, this is known, and therefore everything else is nice. So we get that x minus 4 squared absolute value over 9 is our limit. And now the root test says this will converge if this is less than 1. And so we're going to take this information and use it to figure out what the interval is modulo the endpoints. So this becomes absolute value of x minus 4 quantity squared is less than 9. To get rid of the square, take the square root. Absolute value of x minus 4 less than 3. Now to drop the absolute value, what we can say is, all right, if the absolute value of x minus 4 is less than 3, that says that the inside is between negative 3 and positive 3. So, 3, negative 3 less than x minus 4, less than positive 3. And finally, add 4. So we get that 1 is less than x is less than 7. So, we're almost there. We now know it definitely converges if I'm between 1 and 7. It also tells us if you're below 1 or above 7, you're out. Definitely. The only things we don't know are 1 and 7. So, to finish, we've got to do those separately. So we say, okay, what happens if x equals 1? Well, we get the summation from 6 to infinity of negative 3 to the 2n divided by 9 to the n square root of n. And if you simplify this sum, what do you get? Well, negative 3 to the 2n is the same as 9 to the n. You get a 9 to the n over 9 to the n is 1 over square root of n. Does this converge or diverge? Diverge by what? Yep, diverges by p series. At x equals 7, on the other hand, we're going to get the sum n equals 6 to infinity. 7 minus 4 is 3 to the 2n over 9 to the n square root of n, which becomes the sum from 6 to infinity of 1 over square root of n, which actually is just the same as what we just did, so this diverges by the same argument. And therefore, we see that neither endpoint is included. So this is a case where neither endpoint gets included. Be careful that there's really 4 possibilities. Neither endpoint gets included, both endpoints get included, one endpoint, the left one gets included, or the right one gets included. So you have to test. You really do have to test both points. So our final answer is 1 less than x less than 7. We don't include either endpoint. All right. Find the interval of convergence of the sum n equals 5 to infinity, 6 minus 3x to the n, over n times 3 to the n plus 4. So, let's do what we did before. All right, so we're going to do a root test. So we're going to look at the limit as n goes to infinity of absolute value 6 minus 3x to the n divided by n times 3 to the power n plus 4. We're going to take that to the 1 over nth root. So this becomes the limit as n goes to infinity of absolute value of 6 minus 3x over n to the 1 over n. And here I get 3 to the n plus 4 to the 1 over n. Now, we've already talked about n to the 1 over n. That's going to go to 1. What about 3 to the n plus 4 to the 1 over n? That maybe is not so obvious what's going to happen there. But one thing you can do if you're not sure is to think about ways to rewrite it. Pull out 3 to the n, the highest growing term. So 3 to the n times 1 plus 4 over 3 to the n. And then we're going to take the whole thing here to the 1 over nth power, which is really 3, because 3 to the n to the 1 over nth, times 1 plus 4 over 3n to the 1 over nth power. And now, ask yourself the question, what happens to this part? Well, this goes to 1 to the 0. And 1 to the 0 is not indeterminate. What does 1 to the 0 become? 1. So, this becomes the limit as n goes to infinity of, we've done the limit. We have all the pieces. So this becomes absolute value of 6 minus 3x over 3. So there's our root test, and this will converge if this is less than 1. So we get that absolute value of 6 minus 3x has to be less than positive 3. That says negative 3 is less than 6 minus 3x is less than positive 3. Yes?
Why or how does the thing go to 1 to 0?
Well, so why does this piece go to 1 to 0? The 3 is 3, so that's still there. That's where that 3 is coming from. So just think about what happens as n gets big. So you have a huge number, 3 to the n. That's in the denominator. So that part gets small. So it's 1 plus a small thing, which is going to 1. The exponent is 1 over n. So that's 1 over a big number. So that's going to a 0. Subtract 6. We get negative 9 less than negative 3x less than negative 3. And you're like, we got a negative 3 here. Can we divide? And the answer is, yeah, we can. But if you divide, what do you have to do? You have to flip the signs. 3 greater than x greater than 1. Or if you write that in the mirror image, 1 less than x less than 3. So that will converge between 1 and 3. All right, well, that's progress. Cool. All right, but what about 1? What about 3? Well, let's do 1 and 3. So at x equals 1, we get the following. This is the summation from 5 to infinity of 3 to the n over n times 3 to the n plus 4. We say, okay, well, what can we do? Well, what we can do is say, what's true about this? Well, we can do limit comparison with what expression? Well, here, notice that what you can do with your 3 to the n's is if you move the 3 to the n down, this becomes 1 over n times 1 plus 4 over 3 to the n. So really, what does it look like? It really looks like 1 over n plus a little bit. So it's a little bit smaller than 1 over n. Is it smaller than 1 over n, or is it bigger than 1 over n? I always have to think about these things. I'm getting old. You young people, you're much faster. Okay, but it doesn't matter. I can do limit comparison. So I can do a limit comparison test with the sum of 1 over n because they behave the same way. This part goes to 1. What do we know about the sum of 1 over n? Diverges. So that says that we do not include 1. So that leaves us with 3. So we plug in 3. At x equals 3, this becomes the sum, n equals 5 to infinity. We'll get 6 minus 9, which is negative 3 to the n, over n times 3 to the n plus 4. We can do the same thing we did up here. The only thing we do is we say, oh, there's really a minus left upstairs. So it's minus 1 to the n over n times 1 plus 4 over 3 to the n. Because the only difference between what we just did was that minus sign. Now, does this sum converge? Yeah. Why does it converge? Alternating series test. Because we have that sign, the terms go to 0, so it converges by alternating series test. So it converges at 3. Now, we do not care how it converges. It doesn't matter whether it's conditional or absolute. We just need to know, does it converge or not? So converges at 3, and therefore we get that our interval is 1 less than x less than or equal to 3. So in other words, 3 gets included in our interval. Okay. Number 10. Find the radius of convergence for 2n factorial squared x to the n over n factorial 2 to the n raised to the power 3 to the n. Ah, what fun this looks like. Okay. We might disagree in a few minutes here. But okay, well, we're going to see what we get. So what are we after? Well, we need to either apply a root test or a ratio test, but we know for sure it's a ratio test because of the factorial. So ratio test says, if I'm going to think about this as our a sub n, so we're going to look at the limit as n tends to infinity of absolute value of a n plus 1 over absolute value of a n. And what's true is that this needs to be less than 1, and we'll use that information to determine what does r need to be. And so, okay, so here we go. I'm going to actually start over here. So this becomes the limit as n goes to infinity. The absolute value, only thing it affects is this x term. Everything else is already non-negative. So we have 2 times n plus 1 factorial squared, absolute value of x to the power n plus 1. Divide that by n plus 1 factorial, 2 times n plus 1 to the power 3 times n plus 1. And then we're going to multiply it by a sub n, or I should say the reciprocal of a sub n, so n factorial, 2n to the power 3n, and we're going to divide that by 2n factorial squared, absolute value of x to the n. So you're always going to see that these absolute value of x's essentially cancel. When I say essentially, you have to be careful with this exponent. If there was a 2n, you'd have an absolute value of x squared. But other than that, you're going to get something nice, something relatively easy to work with. From here, you start saying, all right, let's look for ways to rewrite the expression. So with the n factorials, or anything with a factorial, you just pull off enough terms so that things will cancel. So here I would say, all right, I could pull off a 2n plus 2, because this is 2n plus 2 factorial. And there's 2 of those. There's a 2n plus 1. There's 2 of those. And then there's a 2n factorial. And there's 2 of those. Okay? So that's the first term. I'm really squaring everything as I pull it out. What else do we have upstairs? Well, we have an n factorial. And we have a thing 2n to the power 3n. Downstairs, what do we have? Well, we have an n plus 1 factorial, which I'll pull off a single n plus 1. And then I have an n factorial. So that's my n plus 1 factorial. I also can say, all right, I have 2n plus 2 to the power 3n, but I also have 3 more of these, right? Because there's this 3n plus 3. So I also have a 2n plus 2 cubed. And then I have a 2n factorial squared. Okay, so I've accounted for that. I've accounted for that. All right, so everything's been accounted for. Oh, no, not everything. What did I miss? Absolute value of x. Now everything's been accounted for. Okay, so a lot of this is bookkeeping. And once you can get past the bookkeeping, you'll survive. Hopefully you get past the bookkeeping. Anything nice happen? And of course the answer is yes. The factorials, they're gone. Both of them. Nice. We like that. Does anything else nice happen? Well, actually it does. Look at the first part here. What you have are polynomials in n. So when you have polynomials in n, look at the first coefficient. So if you don't need to worry about lower order terms. So upstairs you're going to get a 4n squared and a 4n squared, which means that it looks like 16n to the 4th plus other stuff. Downstairs, what are you going to get? We're going to get an n times an 8n cubed. So that's 8n to the 4th plus other stuff. So what that says is that these first pieces here, what's going to happen to that? It's going to go to 2. So that part goes to 2. So the only thing that we don't know yet is this part over here. So we're going to do that to the side. So what do we have? We have limit as n goes to infinity. We have 2n to the power 3n over 2n plus 2 to the power 3n. We'll do what we did before. Limit as n goes to infinity. 1 over 2n plus 2 over 2n to the power 3n. So I'm just bringing it downstairs, writing everything to the power. But 2n plus 2 divided by 2n is another way to say limit as n goes to infinity, 1 plus 1 over n. And then here, I have to the 3n, I can think of this as n cubed. So what does this do? Goes to 1 over e cubed. Okay. Phew. Whew. All right. Now that we've made it that far, okay. I think we're doing all right. We're making progress. Life is good. Okay. From here, what's left to do? Well, we put it all together. So we get that this is the limit is going to be, this part goes to 2. This part goes to 1 over e cubed. And the absolute value of x is just absolute value of x. And this will converge if this is less than 1. So you rearrange it and say absolute value of x needs to be less than e cubed divided by 2. And this part right here, this is your radius of convergence. So we're done. Okay, all right. I think that was as bad as it gets for doing our algebra. And from here on out, we'll just coast downhill. Consider the following sum. We have ak where we don't know anything about what ak is. And we have x plus 3 to the k. We know that the sum converges at -7 and it diverges at 4. And the question is, what's the smallest possible interval of convergence and the largest possible interval of convergence? So this one is testing, do you understand about convergence properties? So let's talk about this sum. Where's the center of convergence? Can you see that? So to see the center of convergence, what you look at is you say, when does this x plus 3 equal 0? And the answer is at -3. So the center of your interval of convergence is at -3. So we have the following. I'm going to draw a line here. Here's -3. We know it converges at 7. So I'm going to put 7, it converges. Or sorry, -7, it converges. Now here's the thing about intervals of convergence. If I know I converge at a certain point, I always have to converge anything that's closer to my center. So -7 all the way to -3, I have to converge. But it also goes for the flip side. I just have to be closer than -7 is to -3. So the question is, how far apart is that? And the answer is it's 4. So if I come over here to 1, I say, I'm not sure about 1. 1 is a question mark. But anything closer than 1 has to converge. So this is for sure must converge. It must. Now, I don't know about 1. I don't have information. But if I'm from -7 up to 1, all those points must converge. We also know it diverges at 4. So here at 4, we know it's going to diverge. So that says that everything above 4 also has to diverge. So once you know it diverges at a point, anything past that point must diverge. But the same is also true if you flip. So if I go from -3 to 4, that distance there is an increase of 7, right? So if I go back 7, that would get me down to negative 10. Now, what's true about negative 10? We don't know. But anything below negative 10 has to diverge. So essentially, once I know one point where it diverges, anything further away must diverge. Once I know one point where it converges, anything that's closer must converge. So we get to our questions. What's the smallest possible interval of convergence? Well, the answer is, well, the smallest possible is just only the ones which are forced to converge by what we know. So the smallest possible would be starting at negative 7 and going up to positive 1. But don't include positive 1, because we don't necessarily have to converge there. How do you find the largest? Well, the answer to find the largest is you say, okay, throw out everything where we know it has to diverge. Well, that says we can't include 4 or anything past it. We can't include anything below negative 10, but we can include everything else in between. So it would be from negative 10 less than or equal to x less than 4. And that would be the smallest and largest intervals of convergence. Sorry, what?
Is it equal to 10?
You would include it because you're looking for the largest one. You could come up with something which does converge at negative 10. Yeah, just because it's possible for you to converge at one end but diverge at another end, even though they're equally far away. We've actually seen an example like that. If you go back just 2 problems where we saw where it was possible for it to converge, for example, at 3 but diverge at 1. Right. Well, the thing is, we don't know anything about it. So, but we're saying if it's the largest possible one, it's best case scenario or worst case scenario, depending upon what it is you're trying to do. All right. Now we're getting into the fun stuff. Taylor polynomials. So, find the second order Taylor polynomial for f of x equals sine of 1 minus root x centered at x equals 1. Now, a Taylor polynomial is just a sort of a fancy way of saying it's like a tangent line on steroids. So the Taylor polynomial, if you're at degree 2, well, it would be the function at where you're at, so in this case at 1, plus the derivative of the function at 1 times x minus 1, plus the second derivative of the function at 1 over 2 times x minus 1 squared. Now, if you were to ask for the third one, which we're not asked for the third one, the next term would be the third derivative at 1 over 6. Now, where does the 6? That's 3 factorial times x minus 1 cubed. And so forth and so on. So when you do all the dot, dot, dot to infinity, that's the Taylor series. Here we're just looking for Taylor polynomial. Now, unfortunately, because of the nature of sine of 1 minus root x, we can't just say, oh, it's really easy. We kind of basically just have to grin and bear it. We've got to go through and find the function, find the derivatives, do the evaluation, and get our answer. So we do it. F of x is sine of 1 minus root x. I'll say x to the 1/2. Take the first derivative, f prime of x. Derivative of sine is cosine. 1 minus x 1/2, leave the inside alone, times by the derivative of the inside. So that's going to be minus 1/2 x to the minus 1/2. And I'm going to put parentheses so I remind myself that I'm multiplying here. And then we do it one more time. Second derivative. So, derivative of cosine, negative sine, 1 minus x to the 1/2, times the derivative of the inside, negative 1/2, x negative 1/2. And then I still have that second term is still there, so I write it down. And then plus, leave the first term alone, 1 minus x to the 1/2. And then I multiply by the derivative of this second term. Well, that's minus 1/2 times another minus 1/2, x to the minus 3/2. And the good news is, I only have to go here. If I had to go to the third derivative, I'd want a bigger piece of paper. But The next stage is to evaluate. It's really important that you evaluate. It's not going to be a Taylor polynomial if you plug in these actual functions in here. Polynomial means you have to end up with a polynomial. So we're looking for numbers, coefficients. So we plug in 1. Well, the good news is square root of 1 is 1, and 1 minus 1 is 0. So sine of 0 is 0. Cool. F prime of 1, cosine of 0, which is 1, times negative a half times 1. 1 to any power is 1. So you end up with negative a half. Second derivative at 1, well, you're going to get a sine of 0, which means all that's going away. Cosine of 0, which is 1, negative a half, and 1. So that's going to give you a fourth. And therefore, we can use that information and say that our Taylor polynomial is 0 minus 1/2 x minus 1, and then plus 1/4 over 2 x minus 1 squared. And you don't need to do much to simplify here. Don't expand. It's actually to your disadvantage to expand. Almost any time when you're using Taylor polynomials, you really want to leave them as they are. And because if you were to apply them, then you would say, look, let me just plug it in. Here we go. Life is good. Now you might say, how do you apply it? Well, one way you could apply it is to say, maybe I want to do an approximation to a function. I want to approximate what is the function, say, at 1.1. Well, how do I do that? The answer is I plug 1.1 into here. And if I plug it 1.1 into here, it's very easy to carry out that computation. Okay. Number 13. Ah, the good stuff. So, let f of x equal e to the negative 2x. Find p3 of x, the Taylor polynomial of order 3 for f of x centered at 0. Well, all right, that shouldn't be too bad because this is going to have very easy derivatives. So we can actually do the derivatives up here. F prime of x, that would be minus 2 e to the minus 2x. F double prime of x, that would be 4 e to the minus 2x. F triple prime of x, that would be minus 8 e to the minus 2x. F to the fourth. What? Oh, okay, I've already started writing it. All right, come on. F4, well, normally we don't go that far, but all right, of x would be 16 e to the minus 2x. Hopefully that turns out to be useful. And so these are all easy to evaluate at 0. So we can actually just write down the answer. So the Taylor polynomial would be, I'll write down the function in general, f of 0 plus f prime of 0 times x minus 0 plus f double prime of 0 times x squared over 2 plus f triple prime of 0 times x cubed over 6, which we go through, we plug it in. We're going to get 1 minus 2x, because we get negative 2 when we plug in 0 to our derivative. Then we're going to get 4 over 2, so that's plus 2x squared. Then we're going to get negative 8 over 6, which is minus 4/3 x cubed. So that's our answer for part A. Now, part B says what? Well, look at this fourth derivative. Oh, hey, we have it right there. 16 e to the minus 2x. And we're trying to make this fourth derivative bounded. So we want to say, what's the worst it could be? So I'm looking at this function, 16 e to the minus 2x. And I want to look for 0 less than or equal to x less than or equal to 5. Well, if you look at this function, you can see that as x goes to a larger positive number, you'll see minus 2 makes it a negative exponent, which means it starts and then it goes down. So if I want to make this large, where do I look in the interval between 0 and 5? I look at 0. So the answer for part B is we choose m equals 16. Because the best, well, our worst, really, the largest that our fourth derivative could be is at x equals 0, and that turns out to be 16. So m equals 16. Now, why do we care about this part? Well, because there's something called the error approximation. And it's this formula right here, which says that if I want to look at the actual function versus the approximation from the Taylor polynomial, how far off can I be? And this is the formula that gives that expression. Now, the question becomes, okay, well, let's apply it here and find a bound for the maximum difference between the function and the polynomial between 0 and 5. One of the things you might ask, even if you don't say it out loud right now, you might be saying in your head is, would you give us this formula on the exam? And the answer is, yes, we would. If you saw this on the exam, we would say, oh, here's this formula. But you have to know how to use the formula, because just remembering it is only half the battle. You also have to know how to use it. So, how do we use it? Well, we've got to identify m. Oh, well, that's why we did part B. So m is already done. And so, we need to know what is A. Well, no, we know what A is. A is where we centered. See, we're centered at A. So this is A. A equals 0. Well, we need to know n. Well, we know what n is. N is 3. Oh, so we know all this stuff. So what we get is that f of x minus p3 of x is less than or equal to m, which is 16, times x minus 0, absolute value to the power of 4, all divided by 4 factorial. So that's how much our error grows. So, what's the maximum difference? Well, I want to make this worst case scenario, and I say the only thing that can change is the x. Worst case scenario is if I make that x large. So that's less than or equal to 16 times 5 to the 4th over 4 factorial. And if you look at this number, it's actually a pretty big number, which means our error is not great. But we are going all the way out to 5, so that might explain part of it. And we did only go to the third order approximation. There's infinitely more approximations we could have improved on. But that's the answer. So the key is make sure you understand where the pieces come from. Where is this m coming from? Okay, that usually comes from finding that next derivative. Where's your a? That's your center. Which value of n do you use? And once you understand these pieces, you put it all together, the answer pops out pretty quick. All right, number 14. Suppose f of x is x to the 7th, e to the power 6x cubed plus 1, plus 5x minus 4 minus 3 times sine of 2x squared. Find the 40th derivative at 0. There's a hint. Do not try and take 40 derivatives. Now, you might say, but wait a second, wouldn't that give me the answer? Yes, but you would lose it after about 3 or 4, because it is really hard to take 40 derivatives here. You're going to have so many product rules, and things just keep building up. It would probably take dozens, if not hundreds of pages to actually write out what the 40th derivative looks like, and then you have to evaluate it. Now, at this point, you're probably thinking, well, I guess I can drop this problem and move on. No, that's not what you're thinking. You're thinking, oh, cool, there must be a better way. So, the better way is Taylor series. Yes, Taylor series. You might say, but how? Well, the thing is, the Taylor series are storing derivatives. That's how you should think of a Taylor series, as I am storing a bunch of derivatives. So, if I can write f of x as a sum of, well, let's say n equals 0 to infinity of, well, okay, so it's the nth derivative at 0 over n factorial x to the n. So this is the Taylor series for f of x. So the key is I say, look, I want to get the 40th derivative. Whoops. Bad notation. This should have had parentheses here. Sorry. That's a slightly different meaning if I don't put parentheses. All right. You won't tell anybody. Shh. That's just between us. Okay. So what is happening here? I want to get n equals 40. So the question is, how do I pull it out? And the answer is you say, well, I just need to figure out, look at the coefficient of x to the 40. And if I have that coefficient of x to the 40, the answer is that the coefficient of x to the 40 is equal to the 40th derivative at 0 over 40 factorial. So our goal is to figure out what is the coefficient of x to the 40th. So how do we find it? What we do is we build off of known Taylor series. So you should know a couple of Taylor series by heart. So what are the ones you should know by heart? 1 over 1 minus x, you should know that one. That's the sum n equals 0 to infinity, x to the n. E to the x, that's another important one. That shows up a lot. 0 to infinity of x to the n over n factorial. Sine of x, that's the summation n equals 0 to infinity. And now sine is an odd function, so that's the key to remembering. Since sine is an odd function, that means you want to have the ones which are the odd power. So it's x to 2n plus 1, negative 1 to the n over 2n plus 1 factorial. The cosine is an even function. That tells us we're going to keep the even power. So negative 1 to the n, 2n factorial, x to the power 2n. So those are the main ones. Now, on this list, there might be one more which you should probably try to recall. 1 minus x to the alpha is the summation. N equals 0 to infinity of alpha, choose k, x to the k. No, sorry, it's 1 plus x to the alpha. There we go. 1 plus x to the alpha. And that's the binomial series. And I think that was one that you may have just barely touched on. I would say the first 4 are the ones that are the ones you're going to use most often. So make sure you get those down cold. Now, what are we going to do? Well, we're going to take the ones that we know and adapt them. So oftentimes the worst way to find a Taylor series is to use the definition of finding all the infinitely many derivatives. That is a terrible way to find a Taylor series. We want to do them in a slightly better, aka smarter way. So we say, all right, for example here, this e, say I know how to handle e. So I'm just going to modify my e. Now you might say there's a small problem of this plus 1. Okay, we have ways to fix that. Namely, I can write this as x to the 7th, e to the 6x cubed times e. So I can pull that plus 1 out, and then we're okay. Over here you might say, well, that 5x4 minus 3 is going to make it tough. Well, we'll handle that. We'll think of it as 5x to the 4th sine of 2x squared, and then just minus 3 sine of 2x squared. So we're just setting ourselves up for success, because we want to succeed. So what do we have? In the first term, I'll put the e really out front. E times, e x to the 7th. I'm so used to writing e to the x. My pen just naturally goes there. I got to fight it. Fight the urge. Write what's on the page, not what you think is on the page. So e to the 6x cubed. I come down here. I'm going to replace this x down here with that 6x cubed. So the sum, n equals 0 to infinity of 6x cubed to the n over n factorial plus 5x to the 4th, and now the sine of 2x squared, I'm going to come here, but instead of x, everywhere I see an x, I'm going to put in 2x squared. So this will become the sum, n equals 0 to infinity of minus 1 to the n over 2n plus 1 factorial, and then it's going to become 2x squared to the power 2n plus 1. And then minus 3 summation n equals 0 to infinity, negative 1 to the n over 2n plus 1 factorial, and then 2x squared to the power of 2n plus 1. Oh, I'm sorry, I'm running out of space. Okay, but you know what I'm trying to do. Yes? Okay, one more line, and then we'll read off our answer. I'm going to put the powers of x in. So this is e. I'll leave that on the outside. Sum n equals 0 to infinity. I can think of this as 6 to the n. And then I have x cubed to the n, which is x to the 3n, plus 7 more. So x to the 3n plus 7, all over n factorial. Do the similar thing here. 5 summation n equals 0 to infinity. We have negative 1 to the n. We have 2n plus 1 factorial. Here we'll have 2 to the power of 2n plus 1. And then we're going to have x to what power? Well, it's x squared to the power of 2n plus 1. So that's going to become x to the 4n plus 2 plus 4 more. So x to the 4n plus 6. Okay. Minus 3 summation n equals 0 to infinity of minus 1 to the n over 2n plus 1 factorial. And then this will be 2 to the power of 2n plus 1, x to the power of 4n plus 2. Okay, and now I see I chose a bad choice of the 40th derivative, because it's not going to be as interesting as I was hoping for. But that's okay. It doesn't matter. We're here for the process. So what are we looking for? We're looking for x to the 40th power. So we go through and we look on each one of these terms and say, can I get to the 40th power here? Well, let's look at this piece. How do I get x to the 40th? Well, that means I need 3n plus 7 to be 40. When does 3n plus 7 equal 40? That would happen when n equals 11. So I'm going to grab the 40th, the x to the 40th term here will be when n equals 11. So there's going to be a bunch of stuff. And then from here, we're going to have e times 6 to the 11 over 11 factorial. That's times x to the 40th. Now let's come here and say, okay, when do I hit 40? Well, when does 4n plus 6 equal 40? Well, that's when 4n equals 34, and that's when n equals 17 over 2, which means you don't hit 40. So there's no x to the 40th in this piece, which is why I say I chose poorly. Well, how about over here? Well, when does 4n plus 2 equal 40? It's the same as 4n equals 38, or n equals 19 halves. And again, that means you don't hit 40 in that term, which means that when you write out all these powers, there's just a single part that hits x to the 40th. And that's it. Nothing else has an x to the 40th involved in that expression. But remember, what is this? Well, this expression, e times 6 to the 11th over 11 factorial, has got to be equal to that part, because it's the coefficient of x to the 40. So it's got to be equal to the 40th derivative at 0 over 40 factorial. And finally, we just multiply both sides by 40 factorial, and we get e times 6 to the 11th power times 40 factorial over 11 factorial. And that's the answer. Yes?
So how many of these powers should we check in the sequence to see? Are we looking for a whole number?
You have to look for whole numbers. So the answer is what you're looking for is you're looking for any place where x to the 40th shows up in any of your series. In fact, what you're looking is you're looking for all the places where x to the 40th shows up. So once you have your expressions written out, you just say, okay, if it's x to something, you say, what makes that something equal to 40? Which choice of n? And then grab the right coefficients. Yeah, you can.
And then why didn't we check the 2n plus 1 in the series?
Well, we only care about powers of x.
Okay.
So this, too, doesn't matter. So it's just like I need x to the 40th. Because x to the 40th is telling me what this coefficient is. All right. Use known Taylor series. Sorry, it's getting late. Use known Taylor series to write f of x equals 1 minus e to the negative x cubed over x squared as a power series centered at 0. Also find a function, capital F of x, satisfying f prime of x equals little f of x, and f of 0 equals 1. You can leave your answer in the form of a series. So we say, well, what do? We know series. So we know in particular e to the, I'll call it z for right now. That's the summation n equals 0 to infinity of z to the n over n factorial. So that's our basic rule for e to the z. It's actually a really beautiful fact and gets used quite a lot in lots of different settings. So what we're going to do is we're going to just start with our expression. This is our known Taylor series. So we're going to start and look at that. And notice that we did it centered at x equals 0. So we're going to have 1 minus e to the minus x cubed over x squared. That's going to be 1 minus the summation n equals 0 to infinity. But now what I'm going to do is I'm replacing this e to the negative x cubed by a series, and I'm going to replace everywhere I see a z, I'm going to put a minus x cubed to the n, divided by n factorial. Then I'm going to divide that by x squared. Now, this looks unpleasant because it's like, oh, hey, you're in trouble. You're dividing by x squared. That might be a division by 0. But let's be careful here. If you think about it, what's the first term in this sum? So if you look at the sum of e to the z, the first term, n equals 0, is 1. And then you have the next infinitely many terms. But it starts with 1. So what you can do is you can say, oh, the first term in this sum is a 1. And see how there's a 1 there? I can cancel those 1s. So this is minus the sum, n equals 1 to infinity, of minus x cubed to the n over n factorial over x squared. So this is, it can feel subtle when you see it the first time, or like I've cheated. I want to be clear, I haven't cheated. What is really happening here, there's an intermediate step, which is the following. What's happening is we're taking this original sum, minus x cubed to the n over n factorial, and we're saying, hey, you know what that really looks like? It really looks like pull the first sum off, and then you have everything that's left. Well, if you pull the first term off, then everything that's left starts at 1. So that's what was going on. And then we said, oh, look, the 1s cancel, and so we're left with this minus. So we were pulling off the first term and canceling it out. So now, that's a little bit of algebra aside. What do we have? So this is our function f of x. Well, so we get that this is equal to, I can bring this x squared in. And how does that go in? Well, minus the sum, n equals 1 to infinity. I can think of this minus x cubed to the n as minus 1 to the n. Then x cubed to the n is x to the 3n. And this x squared comes in as a minus 2. And then I divide by n factorial. And this answers the first part. Here is a power series. It's centered at x equals 0. And it is the power series for this function f of x. Okay, so we're done with part 1. Now, if it feels like I haven't done enough work, that's because we put all our work into finding the Taylor series for e to the z. And once we had that, using it was a freebie. So we took advantage of the fact that we got a freebie. Okay, so now there's a second part. There's an also. So let's do the also. It says also, I want to find an antiderivative of this. So if I want to find an antiderivative, how do you find an antiderivative? Yeah, you integrate, right? So the nice thing about power series is that you can integrate each term individually. So we have our function f of x. If we take the integral of f of x, so we're really integrating minus the sum, n equals 1 to infinity, minus 1 to the n, x power 3n minus 2 over n factorial. So the important thing here is that where it converges, and by the way, do we know where this sum will converge? Just out of curiosity. Everywhere. Because the only place we used the sum was the exponential sum. The exponential sum converges everywhere. So we can really, the nice thing is we can push the integral in, and so we can say, look, just integrate term by term. So we get sum n equals 1 to infinity of negative 1 to the n. Then we're going to get x to the power 3n minus 1, because I'm going to add 1 to 3n minus 2. Then I have to divide by that power 3n minus 1 times n factorial. And of course, when you integrate, what's the last thing that you need to do? Plus c. Now, we need to figure out what c is. So the way we do that is we say, okay, let's use what we know. We know we want f of 0 to equal 1. So this right now, this is capital F of x. So we plug in 0. So we get 1 equals f of 0. When you plug 0 into the sum, what do you get? You get 0. Because 0 is a very nice number. So we end up with just c. So that says c equals 1. So the final answer for part 2, capital F of x, I'll put the c in front just for aesthetics, 1 minus the sum, n equals 1 to infinity of minus 1 to the n, x to the power 3n minus 1, divided by 3n minus 1 times n factorial. So there's the little f of x, and then there's our capital F of x. Okay, so we can work with power series one term at a time. Number 16. Use the first three non-zero terms of the Taylor series for g of x equals x cosine of x cubed to estimate the integral from 0 to 1 of x cosine of x cubed. Well, you can do one of two things. You can, first off, actually do the Taylor polynomial for x cosine of x cubed and take three derivatives. It's not impossible. It's not fun, but it's not impossible. Or you can say, hey, you know what? I know something about cosine. So cosine of z, that's the sum, n equals 0 to infinity of negative 1 to the n times z to the power 2n, because cosine has the even powers, over 2n factorial. Now the reason I would say you don't actually stop at three derivatives, you have to keep going until you get three non-zero terms. So it's going to take a while. Let's figure out what it would actually end up being. So x cosine of x cubed is x summation n equals 0 to infinity, negative 1 to the n, x cubed to the 2n, divided by 2n factorial, which is x summation n equals 0 to infinity, negative 1 to the n, x to the 6n, because cubed to the 2n you multiply, over 2n factorial. And bring that x through, you get this is the summation n equals 0 to infinity of negative 1 to the n, x to the power 6n plus 1 over 2n factorial. So we write down the first three terms from this series. So n equals 0, negative 1 to the 0 is 1, x to the 1 over 0 factorial. So this is x. For n equals 1, we're going to get a minus. Then we're going to get x to the 7th power, which is 6 plus 1, divided by 2 factorial. So minus 1/2 x to the 7th. Then for our next term, we would plug in n equals 2. So minus 1 squared is a plus. We're going to get x to the power 12 plus 1, which is x to the 13th. And then we're going to be dividing it by 2 times 2, which is 4 factorial, which is 1 over 24. And then there's other terms. So this is the first 3 non-zero terms. So if we had said, well, let's just keep taking derivatives until we end up with getting 3 terms which were not 0, we would have only had to go up to the 13th derivative. Only. Yep, we could have stopped at that point. Which you may or may not be able to fit that on 2 or 3 sheets of paper, depending upon how small you write. The size at which I write, I could not fit it on 2 or 3 sheets of paper. Okay, so we're not done yet, but the point here is we're going to use this as an approximation to the function x cosine of x cubed. Because one of the things that you hopefully are convinced by this point is that integration is really tough. Like most of the functions that you see, you cannot actually integrate. So what we can do is we can approximate. So we can say, hey, I can approximate this function on the inside, x cosine of x cubed, by its Taylor series up to some point. So I could say that's x minus 1/2 x to the 7th plus 1 over 24 x to the 13 dx. All right? Now, the reason we do this is polynomials are perfectly great to work with. We like polynomials. They're the kind of things we like to take home to meet our family. So we just integrate the polynomial. That's 1/2 x squared minus 1/16 x to the 8th plus 1 over a big number, 14 times 24. You can just leave it as 14 times 24, x to the 14th. And you evaluate this from 0 to 1, and you get that this is approximately 1/2 minus a 16th plus 1 over 14 times 24. And that's a good approximation. In fact, it's a fairly reasonable approximation. It turns out this is alternating, so it's within 0.03 of what the true answer is. Now you might say, well, what if I wanted the true answer? Exact value. Could we do it? And it says, well, maybe. How could we do it exact? I know this is not the problem, but let's just throw it in for fun. If we wanted exact, what would we do? Yeah, we'd get infinitely many terms. So you can do this. You can say, look, integral 0 to 1, it's exactly, you replace it by the sum, n equals 0 to infinity of negative 1 to the n, x to the power 6n plus 1 over 2n factorial dx. And the nice thing is you can swap summation and integration where it converges, but cosine converges everywhere, so you can swap integration and the summation. So this becomes the summation, n equals 0 to infinity, negative 1 to the n over 2n factorial, then the integral 0 to 1, x to the power 6n plus 1 dx. Well, that's actually a pretty simple integral. In fact, so simple, I'll just do it in one step. So what's going to happen with this integral is you add 1 to the exponent, and then you divide it by your exponent. So it'd be 1 over 6n plus 2. And then what you would do from there is you'd have x to the power 6n plus 2 evaluated from 0 to 1. But when you evaluate that, you'll end up with 1. So this is the exact value. Now, you might say, well, that's great. Why don't we use that? Well, of course, the problem is you actually have to find the sum. And that's tough. Finding sums are tough. There's very few things we can find the exact value for. But the point is, we can get as much accuracy as we want. We just have to decide how far out in the sum do we want to go. Okay. Well, speaking of finding the exact value, we return to where we began. Find the exact value of the following sum. N equals 1 to infinity, root n to the power 2n minus 1 over 3 to the n times root n squared. Can we do it? I hope so. And hopefully without taking too much time, because I know we're kind of up. So here's some ideas. There's a there's a square there. We're going to take advantage of that, because if there wasn't a square there, we're hopeless. Because look, there's only three things you can do. Geometric, telescoping, and Taylor. That's it. Nothing else. So we say, all right, this is really the sum, n equals 1 to infinity. If we square it, we get n over 4 to the n, because I'll square both top and bottom. Then we'll get some cross terms. Now the nice thing about the cross terms is that the square root of n's cancel. So we're going to get minus 2 times 1 over 6 to the n, because we have 2 to the n times 3 to the n. And then you're going to get a plus 1 over 9 to the n times n. Okay, so that's what we have to find. Now, one of these is straightforward, and the other ones will require a little bit of work. Which one is straightforward? The middle one. So that one is going to be really nice and clean. And the other two will work a little bit on. So let's start by some simple facts. Whenever you see things which involve essentially polynomial expressions, either in the numerator or denominator, and you have to say find the exact value, it's like, oh, we want to manipulate something we know that looks like something geometric. Now you might say, why are you thinking geometric? Whenever you see something like this, so this is really like n 1/4 to the n, you should think of it as like, oh, that's like nx to the n, where I plug in x is 1/4. And down here, it's like, oh, I should really think this as 1 over n times 1/9 to the n. So this is really like 1 over n x to the n. So we should be saying, so we should really think of these as series, and we want to manipulate them. So we start with our really basic one, x to the n. We know that the summation from n equals 0 to infinity of x to the n is equal to 1 over 1 minus x. That's the geometric series. It's the bread and butter. I mean, if you leave calculus knowing only one series, this is the series to know. If you leave with two, also know e to the x. So those are the two you should remember, because they get used a lot. Okay, so suppose we have that. And the question is, suppose I want to get an n down here. How to do it? Well, we think of an operation that makes n come down, and the answer is take a derivative. So we start here, we take a derivative of both sides. We'll get the sum n equals 0 to infinity of n x to the n minus 1. Take the derivative of the right-hand side, because we have to take the derivative of both sides. Well, the right-hand side, if I think of this as 1 minus x to the minus 1, the minus 1 comes down, 1 minus x to the minus 2, and chain rule, another minus 1 comes out. So this becomes 1 over 1 minus x squared. And if I multiply by x, I get that the summation n equals 0 to infinity of n x to the n is equal to x over 1 minus x squared. Okay, so there's a fact. So let's talk about our three sums. We should actually pull our three sums out. So we have minus 2 summation n equals 1 to infinity of 1/6 to the n. That's our middle sum. And we said we could do that. Let's actually go ahead and do it. So that's minus 2. Now be careful. We're not starting at 0. So it's not just 1 over 1 minus the 6. You have to account for the shift. So the way you account for it is you put, where's your first term in your sum? Well, our first term would be n equals 1, which would be 1/6. So it's negative 2 times 1/6 over 1 minus 1/6. And if you multiply this last piece here, this would become, well, it's 1/6 over 5/6, which becomes 1/5. Okay, so we have negative 2/5. That's the middle sum. This first sum, n equals 1 to infinity of n times 1/4 to the n. Well, notice n equals 0 doesn't matter, because if I plug in n equals 0, I get 0. So this actually matches this sum here for what value? Well, 1/4. Because if you plug in x equals 1/4, this is the sum you get. So we get that this is equal to 1/4 over 1 minus 1/4 squared. So 1/4 over 3/4 squared, which is 1/4 over 9 over 16. All right, 1 over 4 times 16 over 9. So you can get at least a little bit of cancellation. So you get 4 over 9. So that's our first sum. All right, so we've gotten, the middle sum was geometric. The first sum, we used differentiation. Now we come to our last sum. Oh, our last sum. How are we going to do that? So we need to bring down in n. We integrate. Yes, we're going to integrate. So here we go. Let's play around with it for a second. Sum n equals 1 to infinity. I'm going to think of this, 0 to infinity. I'm going to integrate both sides. So if I integrate x to the n, that becomes x to the power n plus 1 divided by n plus 1. And that's going to be equal to the integral of this side, which is natural log of 1 minus x. Well, almost that. What's wrong? There's a negative there. It's a negative natural log of 1 minus x. Now, at this point, you're like, "Mwahaha, Steve, it's not going to work because there's an n plus 1. We have ways of making it work. So here's our way. This is, it's kind of a fun technique. It's called re-indexing. So essentially what I'm going to do is I'm going to change my name. So I want to call n plus 1. N plus 1 is the new n. So what does this become? Well, it becomes the sum of x to the n over n. Where does my sum start? Well, if little n was 0, what is big N? It's 1. And if little n is infinity, what is big N? It's infinity. So I get the sum from 1 to infinity of x to the n over n is equal to minus log of 1 minus x, because indexing has no effect on this other right-hand side. Now notice what's our last sum. Our last sum is 1 to infinity of 1/9 to the n over n. It's the right form. So that's equal to minus log of 1 minus 1/9. So that's minus log of 8/9. And in case you're wondering, shouldn't it be a positive number? It is actually a positive number. Because log of, if you're below 1, in between 0 and 1, log is negative. So negative of a negative makes it a positive value. So it is actually a positive value. And so now we've actually accounted for each one of the 3 pieces. So our final answer is we just add these 3 parts together. So you get 4/9 from the first piece, minus 2/5 from the middle piece, and minus log of 8/9 from the last piece. And that is the exact value of that sum. And that's our end. Woo! All right, good times. So hope you do well on the exam, and we'll see you back for the final review in a couple weeks.